Well, hello everyone, welcome back to Zombieland Gaming. This is episode number 6 of Turing Complete. We are actually into the building a working computer portion of this. But first things first, we got to cover a couple things that were left down in the comments. One by a person named Zen Dragon, which for some reason their comment showed up in my notifications but didn't show up on the video. And his actual channel I could not find, so not really sure there, but I did actually catch what he was trying to say, so I went ahead and did some stuff and things with that I will explain, and that has to do with the counting signals portion. So let's go ahead and get on into that. Let me see, which one is it right here? Right, counting signals. Okay, let's close out of this. So let me go back to my original schematic. Was it this one right here? Yeah, right. So I think this is it. Was this one it? Hold on. Is this the working one? I don't remember which one is the working one. Let's just quickly step through it. Nope, that's not the working one, so it must be the default. Does this work? Yep, okay, that one works. Okay, so we have this big, giant, messy thing, right? I mean, this works, and I did work it all out, and this was, like, based on just a very, very basic truth table. Obviously, this is very messy, and we could do this so much simpler, and Zen Dragon kind of sort of clued me into it. I had to do a little bit of research and kind of work this out for myself, but I have titled it his name just because he was the commenter that I had. I'm sure other people have figured this one out, but look at this. Wow, so much simpler. So part of my trouble is a lot of the resources that I'm using don't account for exclusive OR gates, even though a lot of it uses just 2 input gates. It kind of sticks to just AND, NANDs, ORs, and NORs. So I tend to forget about looking for exclusive ORs. So this thing is wonderful. This thing looks like a squid. I kind of like it. So it works perfectly, right? So if we just step this through, we'll be able to see and reason out why this actually works. So if we click on the next tick, right, everything is turned off. So this AND gate has a 0 and a 0 at the beginning of it. So its state is going to be off. We've got a 0 and 0 coming from 3 and 4. Once again, 0. Neither of the inputs are exclusively on. So no inputs out of that. Henceforth, the same coming here, right? We go to tick 1. Now all of a sudden, we don't have a condition that's going to make this AND gate turn on. We only have one input coming on from line 1. But this line going down to the first exclusive OR, 1 is exclusively on, so we get an output from this exclusive OR. 3 and 4 are not exclusively on, where they're both turned off, right? So we get no output there. So when we come out from this 1 exclusive OR, it goes to an AND gate ORed with the exclusive OR from the 3 exclusive OR 4. So that's not working, but it goes down to this exclusive OR, so we get 1 signal. So let's try and push forward to the 2. So we've got 2 signals on now, input 2 and input 1. So we've got input 1 and input 2 ANDed together. We get a 1 on. Comes out to this AND gate. It's got the AND of 3 and 4 not turned on, so this AND gate won't be opening. But it does come down to this exclusive OR, which is basically looking for the 3 and 4 or 1 and 2. So this exclusive OR gate turns on. Boom, we've got 2 signals showing. So let's push forward to something that has 3. So 3 signals. You can see this AND gate still suffices because our input 1 and 2 is the same, right? But now we've got input 3 and 4 we have to deal with. Input 3 is turned on, but 4 is not, so we don't get this AND gate. Input 3 is turned on, so it exclusively ORs this. So 1 and 2 are both turned on, so that is not an exclusive OR condition. So AND doesn't turn on. This exclusive OR turns on, and now we have both the input number 2 turned on and the input number 1 turned on, because that's what they're going to. The top one is 1, 2, and 4 down here. So that works perfectly. And so now if we step through all the way to the very end, which is where our 4 signal is, get out of my way, you can see that now we meet the conditions for everything, but none of these exclusive ORs are going to turn on because everything is turned on, so there's not an exclusive OR state, so the same thing will happen here as well. But our AND gate up here, because we have this exclusive OR gate and this exclusive OR gate are turned off, nothing's happening with this AND gate up here, it's turned off. So this is going to our 2-bit, but our AND gate up here, which sees 1 and 2 and 3 and 4, boom, we turn on bit 4. Holy crap, what a perfect, beautiful solution. That works perfectly. So that was the counting signals that Zen Dragon had mentioned. And then the last one is due to an update that just happened, saving gracefully was no longer working. So here was my original solution for the saving gracefully, and it worked perfectly. However, when we get to this last step here, this condition no longer works. Not exactly sure why. I need to look at the update information. Oh, hello, go back in there to see what has happened. I think I'm pretty sure these conditionals. I'm pretty sure these conditionals were here before, where it doesn't matter if A or A prime or on or off. I don't remember if those were there before. We'd have to look back at one of my prior videos to see if this portion was as part of the set reset. So this no longer works. So the solution that I worked out, and this was Boris. Boris, I forgot your last name. I will make sure that this new circuit gets updated with your name in it, as well as you will see his comment, because his comment actually is in the YouTube channel there. He said he was going to give me a link to his solution, and I still want to see that. I would love to see your solution, Boris. But for the time being, this is what I did here. So basically all I'm really doing is kind of demuxing when it comes down to it. We've got two inputs, and for the conditions, right, it basically says the set reset latch contains one bit of information, but in a manner that is not very easy to load and or save. Create a circuit that can save one bit of information. The first input, which is this one up here, determines if we're going to load or save. So this right here, one of the AND gates is going to be my load. The other AND gate is going to be my save. And then the second input is the value to save. So all I'm doing here is I just took this save value and I just knotted it. And for that basically clears up this last bit here. So we're going to watch this step through. And you're going to see that in the first case, everything is turned on right. So this AND gate is not working. So we're exclusively saving. Step to the next bit. Now nothing is turned on. We get nothing's changed coming out, right? So then we change this up, and so now we are no longer saving that piece of data. The value is now turned off. So this NOT gate allows me to utilize this AND gate. I'm basically just switching here is what I'm really doing. So if we step on through, you can see it all works. We get to this last bit right here. That was the portion that I was screwing up. So because I've negated this input value, now we're guaranteeing that we're loading what was saved in there last. Hold on, I should probably go to that last bit here. Let's step it back to right here. So you can see that we have this output coming here. What ends up happening is this output flip-flops, and so we end up getting the Q naught bit on, or the A naught bit on, whatever they want to call this, you know, for right here, this opposite of A, so A naught. It basically toggles to here, and we don't have this connected to anything. And even if I did have this connected straight to the output, it would screw up the rest of this. So this just enables me to basically negate the way that their circuitry is working. So that was my hot fix for that, and it seems to work. I don't know if it's going to continue working in the future, but it seems to work fairly decently. So all right, so that was the current updates of stuff and things that people clued me in on that were wrong. And now we are up into CPU architecture. So some of these I'm sure people are going to have much better solutions for me. Part of my struggle with this and the way my brain works is that the components that they give for us to use, bit or byte components, I want the component that I should have. So you're going to see some pretty messy circuits here. And the reason being is they don't give me a NAND or an AND or a NOR byte component. They give me an OR component for bytes, and they give me a NOT component for a bytes. So essentially all I did for these upcoming circuits is anytime that there's a NOR, a NAND, or an AND, I just use the byte OR and the byte NOT to make a NOR gate, right? A byte NOR gate. And I made the NANDs and the ANDs out of those. So it gets pretty messy, but it works. And so that's the real trick, right, is it works. And what's nice is these portion is going to actually focus on making a component. So from this point forward, a component that we make will be nice and small. So instead of that big messy thing I have, they'll give me a little component, which is cool. So here we go. First one, logic engine. Create a device that can OR, NAND, NOR, and AND two inputs. And these are byte inputs. That's the concern here. It's not a bit input, it's a byte input. The third input will be the instruction. And instruction is just what we call the number that determines what we compute. So basically, it's going to need a demuxing circuit to basically determine, are we going to OR, are we going to NAND, are we going to NOR, are we going to AND, right? So that's what this is asking about. So this messy circuit right here, which is actually not that messy. I mean, it's fairly nice, right? So we've got our instruction bit right here. And so because it's a byte, and we've only got these gates up here, right? We've got bytes, we've got a switch, a mux, which toggles between 2 byte inputs, which this isn't doing. This is a byte input. So I can't really use that for anything. We got the not byte, the OR byte, negator, and then an adder. And then we've got these byte splitters and byte makers. So I'm sure there might be a better way to do this out here because we do have a 1-bit decoder. So I just decided to go ahead and go as simple as my brain would let me work. I put a splitter here, so I split it out, and I'm just using these first 2 bits, and I'm just demuxing them out. So we're basically a 0, a 1, a 2, and a 3, right? Because that's what they're wanting. They're wanting 0 is going to be an OR, 1 is going to be a NAND, 2 is going to be a NOR, and 3 is going to be an AND. So this is basically my switching. This is what's going to be decoding my circuit to say, do this, do that, do this, do that, right? And so you can follow the purple line down goes to this switch, green goes to this one, the pink goes to this switch, and then the blue goes to this switch. I know I cannot remember the commenter's name, but somebody had mentioned that they really don't like using switches, and I highly agreed with their opinion on the switches because it really is something that I wouldn't use. But it helps. The way that this game works, the switch is a perfect component for doing this. You know, it's generating a logic enable disable is kind of what I'm using it for. So I'm enabling whether or not I'm doing an OR, a NAND, a NOR, or an AND. And so then what I have here is we've got our 2 bytes right here, right? And so what I'm doing here is this first circuit, I already have a component for this, a byte OR. So I basically have input 1, input 2 going into this OR gate, and then the switch, if we have our decoder saying instruction is going to be 0, then you're going to output an OR. Cool. So the AND gate, or the NAND gate, mind you. So in order to build a NAND gate exclusively out of NOR gates, you basically take the OR, and I'm going to basically take the 1 input to both gates, or both A and B input of an OR gate. The second byte is going to both of the inputs of another OR gate, and then you just knot the inputs, the outputs, I mean. And so that way, OR knotted is a NOR. We already know that from if you look up here, right? All we're doing is just inverting the output of an OR, so it's the exact opposite. And so what happens there is now it's this or this. So, sorry, this nor this comes into here and gets NOR'd. And then that goes to another NOR gate to reverse the input again. I might put something up on the screen here to show logically how this works. And then obviously all I have is the switch right coming down here. So a NOR gate, we've already discussed, because that's what we're using to build our NAND gate, is just an OR with a NOT on it. We NOR'd it. There we go. And then the AND gate is basically this last inversion here. We just remove the last inversion, and there we go. We got our AND gate. So, you know, it's this and this is basically what we're doing. And we switch it. So I will show a truth table for how all this works here. I'll probably splice it in about now. All right, so like I said, I'm going to splice this on in here. So this is basically NOR logic. So NOR gates or NAND gates are both universal gates, right? So I can build all of the other gates from NAND gates or NOR gates. So this is basically NOR logic. So we know this is the truth table for NOR gates. We've seen this. We've got this component in the game. So now if you look down here and just basically you'll have to pause the video, but you can see here's the truth table showing the construction of a NOR gate that is equivalent to a NOT gate. Right below it, we've got the equivalent of an OR gate using NOR gates, which is kind of silly to be honest because we have an OR gate byte in our program. AND gates right here. Here's the truth table showing that you can use three NOR gates to make an AND gate. And then a NAND gate, all we're doing is just another inversion on the output of the one right above for the AND gates. So that gets us a NOR gate. So it's 4 NOR gates is going to get us a NAND gate. And then we're not using this in this current level, but here's the exclusive NOR. you can actually use NOR gates to make an exclusive NOR. And then also you can do an exclusive OR, obviously, right? Because an exclusive NOR is just an inversion of an exclusive OR. So there you go. So definitely pause the video. You can take screenshots of that if you want to. But this is just Wikipedia, wikipedia.org. I mean, all I did literally was typed in NOR logic, and boom, that's what popped up. So hopefully that helps. And hopefully this explains what I am doing in the video, because all we have is a NOT byte and an OR byte. So that's all I'm doing, is taking an OR gate and then knotting it to get a NOR gate. And I'm making all the gates up from that. But let's go ahead and step this through, and you can see that my decoder, what they're wanting is they're wanting us to do a Nand function. So we've come up here and we've already seen with this, Nand is a number 1. So we don't have we don't have the OR being used, because we've got these two are inverted to turn off. Or sorry, this one's inverted to turn off, so our AND gate's not satisfied. But we've got our 1 coming in and our 2 is inverted. Bam, we've got our signal coming down here to our NAND gate. And because it's bytes, you can see that this is 218 and 60. I probably could have added an adder. I could have used an adder here. Maybe, I don't know. And now we're going to do another NAND, which is wanting 46. Now we're going to do an OR, so you can see that no inputs are turned on from our decoder. So these two get inverted. This AND gate gets satisfied, coming down here and enabling the output of this OR gate. Boom, we got our 254. Now we got our AND circuit, same thing, right? Coming down here, this is our AND. So everything is turned on our decoder. So the only satisfied AND gate is this one, coming all the way down here to this switch. And then we've got our AND gate coming out, and boop, 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 going in. And so on and so forth. A little bit messy, but it works. So that's what that circuit looks like. If somebody has a much better way to do the decoding up here and to do the a version of the ANDs and NANDs and NOR gates, please let me know. I think the OR and the NOT is sufficient for the NOR gate, but the AND and the NAND, I would love a much better version of that. So please let me know if you have a version of that. Moving on to Arithmetic Engine. So now what we're going to do is the circuit that we had just prior, we're just going to add and subtract. Those two functions are going to be added to this. So all I've done up here is now my decoder has become bigger. So now we have to add the 4-bit, because now we need to have, as you can see up here, we're going to have the number 4 and the 5. Before we had 0, 1, 2, and 3. Or 2 bits right there. Now we have to add that 4th bit to get a 5 and a 6. So all I've used is 3 input AND gates, because I'm not worried about 6, 7, and 8. Those aren't even being used. So I don't need to worry about having 8 AND gates down here. Or sorry, 6 and 7. I should say 6 and 7. 6 and 7 aren't being utilized, so I don't need to worry about those AND gates. If we happen to have the 2 and the 4 turned on exclusively, it's just not going to do anything. If we have 1, 2, and 4 all turned on, it's just not going to do anything. So all I've done there is this is, binary for 0, 1, 2, 3, 4, and 5. So they all will then just come down to, once again, the individual switches. So you can see my circuit up here is what we just had. And all I did for the addition was I literally added a byte adder. And it's kind of a little bit messy down here because I probably should have color coordinated it. But we've got this AND gate comes all the way down here, if we can follow my mouse. So this is my AND line, this is my subtract line. So if we follow the AND line down, it's basically just going to enable the switch that lets input 1 come into the top part of the adder, or sorry, the middle line of the adder, and then input 2 would be enabled to allow it to go to the bottom part of the adder. And then to subtract, literally all I did was I took the switch for A, and I negated the switch for B. So we've got a negation right here. And as long as subtraction is turned on, it will enable this switch, allowing the negated second bit to come in, and it'll basically just subtract. Because we've learned that through our subtraction circuit, the negative number circuit. So let's go ahead and step this on through. And I probably should color coordinate this to make this a little bit easier. But bam. So it wants us to AND right. So if we look up here at our instructions, AND is number 3. So we've got 1 and 2 on, which is binary for 3. It comes in and suffices. This is 0, 1, 2, and 3. So 3 gets turned on. We follow our switch down. This switch is turned on, and we already know that this is my AND gate circuit from the last component. And then boom, it outputs. So we're just going to AND, we're going to OR. We already know all these NANDs. So now subtract, right? So subtract, as we look up here, is going to be function 5. So 4 and 1 in binary is 5. We turn on this last AND gate, come all the way down here, and you can see that I'm enabling the switch for input 1 to come in, and we're negating input 2. So if we look at this, let me color coordinate this to gray. Is it Control and F? Yeah, there we go. So you can see I got 81 coming in here, and Control and F, Control and F. There we go, and we got 108 coming in there. So what is that in math? I do not know math. 27, right? Yeah, so boom, 27 coming out because it's coming out of this adder right here. Bam, 27. So that's exactly how this works. And then if we step through to an AND function, because we've already seen all the other functions, add. So now you can see that add is on input number 4. So all we have is binary for 4 turned on. It comes up, turns on this AND gate, comes all the way down here, and we enable these 2 switches, which are just, there we go. Which are just these 2, which is 121 plus 32, making 153 through a regular adder. So that is all I've done. Now, when you finish this level, like we'll just go ahead and go through, it will actually put you directly to the next level. And as you can see down here on the bottom of my screen, it gives a component preview. So from this point on, the levels are actually going to make a component for us. So now this right here is an algorithmic logic unit or arithmetic logic unit. So this is a component now that we will never have to build this circuit ever again. So no matter how messy you have built this circuit, if the circuit works, all we're going to have now is, and I don't believe they've given it to us here, it'll be in the next level. We'll just be able to click and drag this over, and it's literally just a tiny little, I mean, it's smaller than this splitter up here. And so we'll be able to do all of this functionality all within a small component, which is amazing. So let's go up to the level map, and I think they talk about it, yeah, right here, component factory. Does it give me some, yeah. Welcome to the component factory. The circuits you create here will be usable as components in architecture levels. The circuitry you create defines the behavior of the component, and the layout defines its shape. Components can be added, renamed, or deleted using the usual level save system. Since this level is a tool and not a challenge, you can go to the level map and continue on when you want. And I don't believe, yeah, see, they haven't added it in here yet. So there we go, that's that. So now we're gonna move on to registers, and we'll save the decoder for last. And we're just gonna do these 2 right now. Time to create your master project, implementing the Overture computer architecture. So their computer architecture is apparently called Overture. There's like the von Neumann model and some other stuff. It's been a long time since I looked at like computer architecture, but I do remember von Neumann being one of them. And I can't remember if that was where your registers were like on either side or your registers were stacked on top. And it's a whole way of like how you put your stuff so it goes out onto the bus work in the most efficient manner, as they particularly thought that it was the most efficient manner. This will be an actual Turing complete machine, a true computer in every way. Computer really just has to ins outs. Okay, there we go, that's a computer. A light switch is technically a computer, really, but it's not Turing complete, but it's a computer because you know, data goes in, data comes out. Turing complete means that it can kind of do more functionality and actually think on its own almost. I have locked the red components of this level in place since you always make a mess and don't leave enough space. The mess you make from now on is saved between levels. You no longer get to start fresh each level. So in this level, you need to create a circuit which can copy from a source to a destination. The instruction byte, which is this thing up in the top left corner here, in this level determines the source and the destination that you're going to be loading to and from. Bits 1, 2, and 3 give the destination. Bits 4, 5, and 6 give the source. Source and destination can be one of 6 registers. We will name the registers register 0 to register 5 respectively. Additionally, this map is dedicated input component, which can be the source, and an output component, which can be the destination. And these are actually down right here. So this is my source, and this is my destination. So they're kind of giving you an idea of this is the binary for how we're going to instruct which thing we're going to. So the source is going to be basically 0, 1, 2, 3, 4, and 5 in binary. And then 6 is going to mean that you're going to source the input. And then 7 is just not used at all, so we don't have to worry about it. And the exact same thing for the destination. And then to get a more intuitive understanding of the requirements, click the instruction icon in the upper left corner. Finally, the input and output components now have an additional pin. Set that pin to on when you want to read from input or copy to output. So if we come up here to where it says instructions, it's the little wheel up top. So we can basically see that, if we copy or calculate, and, it'll tell us, what we're doing here with any of our instruction stuff. So this is our first real addressing to tell the computer what the hell to do. Are we just copying, or are we going to calculate something? If we're calculating something, we already know that we have these different instructions because that's what we just built a circuit for, right? And if we're going to copy, then we're going to say copy from the input to register 1 or copy it to register 2, right? So you can kind of get an idea of what these are going to be doing. So this is actually a relatively simple circuit. It looks like it's big and messy, but it's relatively simple. So all we've done up here is we actually have our decoder, right? So we've got a 8-bit decoder. So what we basically are doing is this is our destination, bits 1, 2, and 4, bits 8, 16, and 32, as we saw from, does it say? Yeah, bits 4, 5, and 6, right? So 4, 5, and 6 is going to be 32, 16, and 18 is going to be our destination, and bits 1, 2, and 3, or 1, 2, and 4 in binary, are going to be our source. So all I've done is taken these 3 bits to a decoder, which means I don't have to worry about making a whole bunch of AND gates. I actually have a bit decoder here. 3 bits in, 8 bits out. We don't need to worry about this 8th bit because it's the unused, as we saw in here. Let me see, where does it say it at? Right here. See, if all of them are turned on, it's unused, so I just don't connect it. Doesn't have to worry about it. If we look at the actual decoder itself, you can see the top bit here is just a disable bit, this little pin right here. Don't need to worry about it. We're not disabling anything. So all I've done is simply taken, this is my, going to the save, right? Yeah, so the middle pin on our register is save, the top pin is load. Hello, can I see that again? And then the bottom pin is our value. So all I've done is connected all of these input value pins directly to this line that I have just going between, you can think of this as my bus from the input to the output is my bus line. And all I've done is taken the bus line to each one of these value inputs. And then all we've done is taken from our decoder. We can tell that the way that they wanted this to be worked is right here. Register 0 means nothing's turned on. Register 1 means bit 1 is turned on. Register 2 means bit 2 is turned on. Register 3 is bit 1 and bit 2 turned on, so on and so forth. So that's all I've done is taken this is nothing turned on, boom, it goes to register 0. And I was hoping that this is how they were going to be. Register 0, register 1, 2, 3, 4, and 5. Thankfully, that's how they were. Makes it nice, neat, and orderly, tidily. So we got register 0 save, register 1 save, register 2 save, so on and so forth. And the exact same thing for the loading. The instruction is the exact same way. So we've just got the top bit means nothing is turned on for loading. Goes to register, load register 0. And then for the output, all I did was just connected all the outputs together straight to the output line. And this line right here that's connecting them, you would think that this needs to go away. But I want to be able to, if we have bit 6, bit 6 turned on here, then we want to make sure that we are... not bit 6, but sorry, binary 6 turned on. Then we want to make sure that our input is turned on or our output is turned on, and then just direct, because it's not going to a register, right? We're just taking input directly to the output. So we need to make sure that we connect this up right here. Bam. Well, that's fine. Whatever. Thank you. So, all right, let's go ahead and step this through and look at how this goes. Oh, plus, here we go. Look at this. You can see I've got some components here. Look how small those are. That big, gigantic mess of crap that I had in that last circuit, look how small it is. So it doesn't matter how messy and crappy you make it. If it works, it works. It's that small. I love it. All right, okay, boom. Let's go ahead and step this through. All right, so it wants us to copy input to the output. So it's giving us the instruction here of bits 4 and 2 and 32 and 16 are turned on. So we know that we're going from our input to our output, and you can see that I have my lines going here. Enabling, we can look at this output here. We've got a disable enable bit is on the bottom. So you can tell we're going from our input directly to our output, and none of our registers are turned on, so it doesn't give a crap about the data. Next bit, it wants us to copy 33 from the input. So even though we've got 33 going to the output, it doesn't matter. We're not actually reading that output, but that 33 is coming up the line up here to this register, which we have the copy, which is, save turned on. Boom, because right here, if we look at this, you can see save as my middle pin. Save is turned on. Cool. I got 33 saved into my register. Step to the next one. Copy register 0 to register 1. So you can see that now we are loading the output right here of register 0 to register 1. So we've got register 0 is loading. We're taking this information out, coming back up, and boom, putting it right back into register 1 because register 1 save is turned on. Pretty awesome stuff. So we're basically giving ourselves a way to store information. And this is basically just now stepping through. You kind of get the idea. It's going to be the same pretty much for everything. It's a pretty relatively simple circuit. And step all the way through. Done. Awesome sauce. Oh, and we got another entry in our book. What does this entry say? Which one was this? Oh, the bus. The bus is a circuit that allows data copying between components instead of having every component connected to every other component. Connecting individual components only to the bus greatly simplifies circuits. Wow, that was a mouthful. You likely made a bus that looks somewhat like this, connecting input, output, and registers. Yeah, so it's basically just showing that we have everything connected in one way. Cool beans. So that is registers. We now have a register, which is amazing because they're actually going to give us a register in the next section. So that is now component factory and registers. And the last one we're going to deal with today is going to be this one right here, which is a decoder. And you have seen me basically build this. So we are now going to give ourselves a decoder specifically for register instructions. So the circuit you built in the registers level can copy values between registers, while the arithmetic engine can do different operations on 2 inputs, but need to be able to do both in the same circuit. To do this, build a decoder which will decide which mode our computer is in based on the 2 bits we haven't used yet. So we have not used the 64 and 128 bits, the 7 and 8 bit, right? So what they're showing you here is that what these 2 bits are going to do is going to be immediate, which means do it right now. Calculate, which is going to be the and, the or, the nor, and the NAND, or add and subtract. Copy is going to be using our registers to save and load information. And condition is going to be something special that we haven't dealt with yet. So here you can see that we've got the green and pink symbol in the middle of the circle. That just means that it doesn't give a crap what the value of that is. It could be any value whatsoever. So here's the circuit I built, and we've already seen me build this before. So we know that it wants us to use, this is a byte input, by the way. Down here you can see this. It wants us to use bit 7 and bit 8, or 64, 128 in binary. And so all I've done is, are these 2 off? Turn these 2 NOT gates on, which conditions the AND, gets us our 0. Is 64 turned on? Uses this one. Is 128 turned on, but 64 is off? Uses this one. If they're both turned on, we use this one. So that's all this is doing. And it gives us our immediate, copy, calculate, and condition. And so now it's saved that to our factory, and now we have a decoder. So that is awesome. So we're getting really close. I think in the next episode, we might cover all 4 of these, possibly. We will see how difficult they are. But hopefully all those made sense. There were actually, really surprisingly, wasn't too much to these components. And it's nice that we no longer have to keep refreshing and starting all the way over from scratch. Now it's giving us components that we can use, which is really awesome. So we've got a decoder, a register, and an ALU component that we have now made. So perfect. I hope you guys enjoyed this. If you have any suggestions about how to make those circuits much better, please go ahead and toss those ideas out to me. I'd like to show them off to everyone else and just show how much more efficiently these can be made, because while my components do work, we can all agree they're not really efficient or compact. So anyway, have a great day, guys. I'll see you guys in the next episode, which is probably either going to be Satisfactory or Minecraft. The month of December is going to be really rough. I've got a ginormous project taking Power Rail from 90 foot in the air on 7 cranes and dropping it to the ground to make it much safer and ergonomic and just much more easy for everyone to work on. But it's going to be a 7-week-long project. I'm heading up 6 guys and myself that are going to be, it's 370 feet worth of 4 times power rail times 7 cranes, and we got to do the concrete drilling and remove the wiring from up above and rewire down below. It's a pretty crazy job. Pretty excited to get it done, but it's going to be a whole lot of overtime days, and I probably won't be putting out too many videos in the month of December. I'm gonna try my best to at least get one out a week. I have some Graveyard Keeper and Forza Horizon 5 videos in the vault, so maybe those ones will be coming out just because they're gonna be relatively easy to edit and get out. So keep on the lookout for that. And like I said, I will keep looking at the comments, and I will try to make sure I'm getting everybody's comments viewed on here with their solutions. Yeah, this has been a lot of fun. So see you guys in the next episode. Ta-ta for now. Bye.